All right, class. So these are the formalizing relations and function notes. So we're going to look at functions in a little more detail. As we already talked about, a function is a relation in which each value in the domain is paired with exactly one value in the range. Of course, the domain is a set of x values, and the range is the set of y values. So once again, the domain is your set of x values that are valid, and the range is your set of y values. So if we look at this relationship here, I have these 6 ordered pairs. I have -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. So the question is this relationship a function? So I can determine if it's a function by looking at the domain and the range. So what I did here was list out the domain of this relationship. So I listed out all the x values. I have -2, -1, 0, 1, 2, and 3. So those are all my x values. And I listed out the range, which is 4, 1, 0, 1, 4, 9. So those are all of my y values. So I list out the domain, I list out the range, and then once I show the difference between the domain and range, I create a mapping. So I have all of my domain values listed. Once again, that's -2, -1, 0, 1, 2, and 3. Then my range values, 4, 1, 0, 1, 4, 9. And then I show the relationship. And once I show that relationship with this mapping, I can determine if it is a function or not. So based on the relationship, -2 goes to 4. -1 goes to 1. 0 maps to 0. 1 maps to 1. 2 maps to 4. And 3 maps to 9. So it appears that every domain value maps to exactly one range value, one unique range value. So this relationship is a function because every domain value maps to exactly one unique range value. -2 goes to 4, -1 goes to 1, 0 to 0, 1 to 1, 2 to 4, and 3 to 9. So this is a function. Let's look at example 2. Example 2, I once again look at this relationship and I identify the domain and the range. So my domain here is 4, 1, 0, 1, 4, and 9. And my range is -5, -3, 0, 1, 5, and 3. So I identify my domain and my range. And I once again create a mapping to see if this relationship is indeed a function. Every x value should map to only one unique y value if it is a function. So based on this relationship, I see that 4 maps to -5, 1 maps to -3, 0 maps to 0, 1 maps to 1, 4 maps to 5, and 9 maps to 3. So right away we see there's a violation. 4 maps to -5, and 4 also maps to +5. So that 4 can't go to two distinct range values. So this is not a function. Also, y maps to negative 3. I'm sorry, 1 maps to negative 3, and 1 also maps to 1. So that's another example of a violation. This is not a function. So 4 maps to negative 5 and 5, and also 1 maps to negative 3 and 1. So those domain map values map to more than one range value. This is not a function. This is not a function. Another way that you can determine if a relationship is a function is by using the vertical line test. Using the vertical line test. So if I use the vertical line test, I very simply just draw a line, a vertical line, through my graph. And I see if my vertical line touches the graph in more than one location. If it touches it in more than one location, it is not a function. If it touches it only once, if it touches my graph only once, it is a function. So for this first example here, graph A, when I drew my red line or my vertical line through the graph, it touches it in 2 spots. So that tells me for this example that this point here that I highlighted is approximately 4, 3.5, and this other point that I highlighted is approximately 4 and 6.25. So clearly we can see that my domain value 4 maps to 2 different range values, 3.5 and 6.25. This is not a function because my vertical line hits that graph in more than one spot. It hits it in 2 locations there. So this is not a function. The next one, graph B, if I draw a vertical line, my vertical line only hits the graph in one location, about right here. So this is a function because that point where it touches the graph at, which is, let's say approximately 2.5, we can see that it only hits that in one location. That domain value only maps to one range value. 2 maps to 5. So this example is an example of a function. Yes, this is a function. So you can use the vertical line test to determine if it is a function. Or you can use the mapping, like we did in examples 1 and 2, to determine if it is a function. All right, so the next concept that we're going to talk about is function notation. Function notation. So we've been used to using equations written like that to identify our functions. Y equals negative 3x plus 1. Now we're going to begin using function notation. F of x equals negative 3x plus 1. That's f of x equals negative 3x plus 1. F of x is going to replace y. So the f of x is going to replace y. The letter f is the name of the function. It is not a variable. So this is red, f of x. So x is my independent variable. F of x is, well, I should say, f of x depends on the independent variable x. So all we're simply doing is I have y equals negative 3x plus 1, and I'm rewriting this equation in function form, function notation, so I'm simply replacing y with f of x. Replacing y with f of x. And then, so when I think about an ordered pair, before I thought about it as x and y, now I think about it as x and f of x, or x and the function of x. So y is being replaced with f of x. So we really haven't done anything different. We're just using function notation now. Instead of using y, we call it f of x. Examples 4 here. I have this f of x equals 4x subtract 12. So before, you would have seen this written as y equals 4x subtract 12. But now we just say f of x equals 4x subtract 12. So if I plug in my domain values, I chose my domain values 1, 3, 5, and 7. If I choose those values and plug them into my function, so 4 times 1 subtract 12. So my function f evaluated at 1 is going to equal -8. Instead of saying y is -8, I'm saying f, my function evaluated at 1 is -8. Instead of saying y equals 0 when I plug in 3, I'm saying f of 3 equals 0, because 4 times 3 is 12. 12 take away 12 equals 0. F of 5 is 8. F of 7 is 16. So when I write these as an ordered pair, I have 1, -8, 3, 0, 5, 8, and 7, 16. So my x and f of x written as an ordered pair would look like that. And of course, once I have them as an ordered pair, I can quickly identify what my range is. My range is simply -8, 0, 8, and 16. Likewise, example 5 is done very much in a similar fashion. My function is g of x equals x squared, or before I would think of it as y equals x squared, now it's g of x equals x squared. If I plug in my domain values, -1, 0, 1, 2, 4, and 16, if I plug in my domain values, I get my set of range values. I have my ordered pairs there, and I can determine what my range values are. My range is 1, 0, 1, 4, 16, and 256. This function g evaluated at -1. -1 squared is 1. That's how I get my range of my ordered pair, -1, 1. If I plug in 0, this g function evaluated at 0 is simply just 0. So I get the ordered pair 0, 0. And if I go down through all of these here, I can find out what my range value is when that function g is evaluated at those domain values. All right, example 6 here. Omar has decided to take yoga classes for 1 year. The yoga studio costs $10 to join, and then each yoga class is $5. Omar's fees can be represented by the function f of x equals 5x plus 10. What are the domain and range values? So if you're given a function, you have to first think about what x values or domain values make sense. So if he's taking classes for a year, we know there are 365 days in a year. So Omar can go for 0 classes, 1 class, 2 classes, 3 classes, all the way up to 365. So those will be the domain values for that function. Does that make sense? The range values will be those domain values plugged into that function and calculated. So if I put 0 into my function, 5 times 0 is 0 plus 10, it will cost him $10 for his yoga classes. If he went to 1 class, it would cost $15. So I will plug that 1 in for x. Simplify. 5 times 1 is 1. 5 plus 10 is 15. It would cost $15. I can go on through it. It would cost all the way up to $1,835 if he went every day of the year.